Okay. So extrinsic. So if you talk about extrinsic, you already have seen about intrinsic, right? So in intrinsic, the current, you will get a current, right? The current would be more dependent on the temperature. Okay, so we already have an intrinsic semiconductor. So why there is a need for an extrinsic semiconductor now? In intrinsic semiconductor, as the current is mostly dependent on the temperature, controlling the temperature is pretty hard. Why it is pretty hard? Because the temperature is something which changes and depends on the environment and a lot of stuff. And also intrinsic, as it depends on temperature, we don't have such an extent like to manipulate it, to set the current or limits of the semiconductor to ourselves is very hard in case of intrinsic semiconductor. Also, in that, as holes and electron levels are approximately equal, the amount of output efficiency it gives is pretty much very low. Okay, so we need some change from the intrinsic semiconductor. So that's why we move on to something called as extrinsic semiconductor. Okay, so in extrinsic semiconductor, what you do is take an intrinsic semiconductor, you will do a dopant there. Okay, well, what is dopant? Basically, it's an impurity. Okay, well, that impurity, we say it as an impurity because you know that the semiconductor is made of uh, silicon, all those four valency stuff, correct? But in case of a dopant, we add not from the same group. We add from a group 5 or group 3. Obviously, it is not similar to the structure, right? It is made up of silicon. It is not belonging to the same group. So the adding thing is called as an impurity there. Okay, so in extrinsic semiconductor, the current will be more dependent on the voltage rather than the temperature, which gives us a more liberty on the controlling stuff of the current flow in the semiconductor. Okay, so as I said, the impurity is called as the dope impurity. While you are adding an impurity, right? That impurity step, adding the impurity step to an intrinsic semiconductor is called as doping, and the impurity you add, it's called as dopant. Okay, so such a semiconductor is an extrinsic. And the typical doping range would be 10 power 20 to 10 power 27 atoms per meter cube. Okay, so all the things are set. And as I said, there are two types of dopants you can add. One is a pentavalent element and a trivalent element. Obviously, the trivalent element will have 3 valence electrons belonging to the third group. Where does a pentavalent element go? It will have 5 electrons in the valence shell and it will go to the group 5. Okay, the same slide. Okay, going to next slide. Yeah, this is pretty much the table. Yeah. So depending on the dopant, I said, right? Either you dope with a group 3 element or a group 5 element. To be peculiar, it's a trivalent or a pentavalent. If you dope with a trivalent element, what do you call it as? Anybody? It's a p-type. Okay, yeah, p-type. If you do it with a group 3 element with a trivalent, it is called a p-type semiconductor. Whereas if you do it with a group 5, which is pentavalent, it is called as an n-type. Okay, well, this is the basic types of extrinsic semiconductor. So why peculiarly this third group and the fifth group, and why not any other element in the periodic table? We have a hell lot of elements, right? The reason for it is, if there is an in the semiconductor, it is made up of silicon. I mean, the group 4 elements mainly, right? If you are adding any other element or an atom which doesn't resemble the shape or which doesn't resemble the properties of the silicon, the structure would collapse. Am I right? If something odd comes into an even structure which is not fitting in it, it would obviously collapse the whole structure. So that's why we are using elements which are very similar in structure and crystal structure to this silicon or group 4 element. Okay, so that's why we are taking a choice of group 3 and group 5, which is very near to the group 4 elements. That's why we are choosing pentavalent and trivalent elements. Okay, so what are the advantages of extrinsic semiconductor? The conductivity is high. Obviously, we will see why the conductivity is high. Either the holes are high or the electrons are high, which carries the current more. Next, as I said, we more we have a freedom of how much controlling the concentration of the doping. We have the control of over the concentration of doping. So essentially, we have whole control of the amount of conductivity it gives or amount of current it generates. Okay, then this is not dependent on temperature. Okay, these are the three main advantage of going into something called as extrinsic semiconductor. Next, yeah. Next, we are going on to N-type semiconductor. As I said, when you dope a pentavalent element or impurities, is called as N-type. Such an example is phosphorus. Okay, so here what will happen? Yeah, I'm coming on. Here what will happen? See, silicon will have 4 valence electrons. Correct? It will form covalent bond around the 4 silicon elements around it. Okay, if I have to say, consider this to be silicon. It will have 4 valence electrons. Another silicon elements 4 would be around it. So it will make a covalent bond with it. And this silicon is host element because it is present in the semiconductor itself. What I do?
Active medium
என்னடா
direct band gap semiconductor active medium. இங்க வந்து நம்ம gallium and arsenic யூஸ் பண்றோம். Gallium
ஒரே
and
செகண்ட்
arsenic
ஒரே செகண்ட் எனக்கு கேட்கல ஒரே செகண்ட் நான் வால்யூம் மட்டும் கொஞ்சம் ஏத்திக்கிறேன் சொல்றேன் ஹலோ
அவன் தெரியாம அட்மிட் பண்ணிட்டான்னு நினைக்கிறேன்.
அப்படியா? Hey, it's
Yeah.
fine, it's fine. I thought it was a doubt. I'm fine. Yeah. Yeah, doubt எதுவும் இல்ல தானே? Yeah, okay, fine. No issues. Okay. So, if what I do, I introduce a phosphorus here. How many valence electron phosphorus has? 5. Okay, so one will go for one silicon, another will go for another silicon, and another silicon. One more electron will be free here. And this electron, as these 4 covalent bonds are formed, the electrons in the covalent bonds are under a peer pressure from another silicon. So it is very hard to remove this. But essentially, the 5th electron, which is very free, is obviously free, right? It is not connected anywhere. So it is very easy to kick off this 5th electron from this. So what happens in normal temperature itself, this 5th electron gets kicked out. So this electron, obviously, it's free. It roams around. So obviously, if an electron roams around, it can carry the current very much faster. I mean, the very much more amount of current it can carry. Correct? So this is the logic behind the N-type semiconductor. This, when happens with holes, now you saw the free electron roaming around and carrying the current. This, when happens with the holes in place of electrons, that is called as p-type. This is the major working process of it. Okay, so to be more on numeric side, the silicon is the host, right? It is having a dielectric constant of 12. So the force is inversely proportional to dielectric constant. So when normal vacuum, it will be 1. Okay, so the force will be strong. But when you have a silicon element with the dielectric constant of 12, you are decreasing the force between this free electron atom and the nucleus of phosphorus by 12 times. Okay, so it is pretty much easier to kick off the electron, right? So that is what in terms of in terms of statistics, if you take it. Okay, so that is what they are explaining. So I mean, from phosphorus, why? Okay. From phosphorus to kick out the 5th electron, the ionization energy is given here, 0.045 electron volt. Okay, so yeah, the same stuff is rotated here. Yeah, here what they will say is, I mean, if the dopant amount is less, okay, let us take, you have 100 silicon elements. You only dope 2 phosphorus elements. Essentially, what you will have, I mean, I have one at one position, phosphorus, and another at 100th position. In between these 2 phosphorus elements, there are 100 silicon elements. Okay, obviously, as the distance is more between these phosphorus elements, as they are less doped, every phosphorus element will try to act independent. It will not have any influence or current influence of the other phosphorus element, correct? Because it is far apart. So that is what they're trying to say. If you have more densely packed phosphorus elements in a particular area, there will be a lot of influences. So the current will also be more. So that is what they're essentially trying to convey it here. So here's the structure. I told now, you will have leave this intrinsic hole. There will be the phosphorus thing will be there. It will donate an electron to the conduction band due to the thermal energy itself. So once leaving the electron, what the phosphorus ion will become? It's a positive element. So you call it as a donor element. Okay, well, the phosphorus is called to be a donor element. So in N-type semiconductor, you get a donor element. And this EDE represents the donor energy level in which the donor element stays. And this donor, obviously, you know, it is leaving electron. So electron will move on to conduction band. As I said, you need very less energy to push it off into the conduction band. Correct? Electron leave panna. So from this statement system, you can conclude that the donor band will be very near to the conduction band. I hope you are getting it. Okay. Next, in this graph might confuse you. So what I say, see the x coordinate. It is 1 by t, reverse of the temperature. So you have to analyze this graph from right to left and not left to right. Okay, we will move from this area. Here, as you see, I mean, if you go around, this n represents the number of electrons which is obviously passing through, okay, or the donor elements present there. Okay, and this is the graph. This is the corresponding bands represented by that. Okay, first at 0 Kelvin. At 0 Kelvin, obviously there will be no movement because there is no essentially heat, right? And also you have seen that this phosphorus electron also, it's need a bit amount of room temperature. So at 0 Kelvin, there will be no movement itself. There will be incomplete ionizations. So you would expect very bare minimum, I mean, just 1 or 2 electrons to be present in the conduction band. Next comes to the temperature. Then we raise the temperature to a certain limit. So once we raise the temperature, what happens? We need very little room temperature to promote these valence phosphorus element, the single electron, right? So what will happen? This will go to the conduction band. As you can see, the phosphorus get positive charge and the electrons from the phosphorus move on to the conduction band. Okay. After a certain limit, you could see this graph getting saturated. Why the graph is getting saturated? As phosphorus is the impurity you add, once after a particular temperature, maybe after the 100 Kelvin they mentioned, what happened? Every electron from this phosphorus would be moved onto the conduction band. There will be no leftover electrons in the phosphorus itself to make a movement to the conduction band. So essentially at the end, after every donor atom donates its electron, it becomes saturated. Then at the third region, which is the highest temperature, you raise a hell lot of temperature, the graph shoots up. What does this say? You know that valence band will have also electrons, right? Valence band will also have atoms. So once you raise the temperature so high that these electrons get agitated and can jump through the band gap itself. It can jump through the whole band gap itself. So that electrons from the valence band shift to the conduction band. So that's why here these graph shoots up. So this graph is clear, right? This is what the whole graph talks about. So what you have to do is you have to go from right to left and not left to right because the x-axis shows 1 by temperature. Okay. Yeah, this is what the whole stuff explains. Also, here see this value 1 by 25th they have given, right? This comes from pretty simple maths. What you will do, you will this is not needed for the thing, but what you will do, you will take the whole energy gap and also the gap needed for phosphorus. So for silicon, it's around 1.1. Okay, for this around 0.45. So you use a formula of these comparing the silicon energy gap with the phosphorus emitting energy gap, you would get a ratio of 1 by 25. So that is what they are saying, that the ionization of an electron is 1 by 25th. Okay, so this is what they pretty much state here. Yeah, everything got discussed. Yeah, so here leave the red ones. It's pretty much already discussed. So we have to make in mind that this N is the electron concentration and conduction band. Okay, so pretty much if you don't, they have also mentioned at low temperature. That is the key point, because at low temperatures, you would have only energy to push the positive ions electrons, right? You will not go into the valence band itself. Okay, So what you can say, the electrons which go to the conduction band, it pretty much same as the electrons lost by the phosphorus or the impurity. Correct? Am I making sense? So if we can represent this, if suppose there are 100 phosphorus and 50 phosphorus gives out its electron, then how much will be left? Another 50 will be left unionized. Correct? This is what this essentially states. Total number of impurity atoms you added minus the total number of impurity atoms that were not ionized. This gives us the electrons which are ionized. Okay, was pretty much the same for different
Kumara.
notations.
Kumara.
Anda.
Career concentration derivation எடுக்கிறியா?
எதுக்கு இன்ட்ரின்சிக்கா?
இல்ல இப்போ you are going to take the derivation ல.
ஏன் நீ எடுக்கறியா? pretty much simple தானே. இன்ட்ரின்சிக் வரும்னு அப்படியே பார்க்கலாம்னு பார்த்தேன்.
அதான் நான் இன்ட்ரின்சிக் சொல்லி கொடுத்தா பெட்டரா இருக்கும்னு தோணுச்சு.
Yeah, sure. நான் நீ வரலன்னு தான் ஸ்டார்ட் பண்ணேன்.
Sure. No worries.
Okay. I'll stop. Just a second.
Yeah.
Okay, guys. இப்போ வரைக்கும் பார்த்தது it's okay. It's pretty much extrinsic ஓட introduction. ஓகேவா? Then we'll move on to the extrinsic derivation. அது நீங்க intrinsic படிச்சு and extrinsic படிச்சா you will get more easier. ஓகேவா? We'll move on to Udhaya now. Udhaya recording only இருக்கும்ல?
Only.
Okay.
Yeah, so I'm so sorry guys, I was having some personal emergency, I could not avoid it. Yeah, so we'll quickly go through what intrinsic semiconductors. I suppose அவனே நிறைய ஐடியா கொடுத்துட்டு தான் extrinsic ஸ்டார்ட் பண்ணியிருப்பான். ஸோ சும்மா ஒரு glimpse மாதிரி தான் இருக்கும், nothing much. Okay, just give me a second to start presenting. Please don't mind the keyboard in the bottom. Okay. Yeah. All right. So semiconducting materials, as we all know, are intermediate materials between conductors and insulators, right? So these conductors have large conductivity. They cannot be modified to a lower extent. Inductors have a lot of resistance, so they cannot be also modified for our interest, right? So in turn, semiconductors are moderate materials that can be better utilized by modifying them. And how do we do that, and what do you mean by the term modifying and all that we see? Yes, so generally in any kind of material, you will have a conduction band and a valence band. Conduction band contains all the electrons that participate. Conduction band contains all the electrons that participate in conduction. That is those electrons that produce current. Valence band are the electrons which are inside. Right? These valence electrons, when they acquire a certain amount of energy, can jump to the conduction band and participate in conduction. But if you observe carefully, in the energy band gap between the conduction band and valence band will be very higher. Yes, and that is the reason why those are not very preferred for different applications. Yes. So what are semiconductors? There's those materials which have almost an empty conduction band and almost filled valence band. Yes. So in that case, what happens here? When you supply very small energy also, they can easily jump to the conduction band and do the conduction process. Just simple values, pure germanium, these are pure values, right? Pure germanium will have energy band gap of 0.7 and silicon will have an energy band gap of 1.1 electron volts respectively. Okay, and then silicon and germanium are very much preferred kind of materials for conducting, especially because of their nature. Yes, what kind of nature? A pentavalent nature or a trivalent nature, which we'll be looking onto. Okay, so let's quickly go forward and see. So this simple periodic table, you very well know that the elements in this fourth column, right, the silicon, germanium, these guys help in doing this process because they bond covalently and they bond kind of differently in such a way that when you have an extra electron and they jump over, you create a hole there, right, in such a way that they'll keep jumping to the conduction band and helping in conduction process. Okay, so how does this covalent bonding work and all that? So if you see carefully, if I'll be able to rotate this, just give me a second. Okay, anyways, so what happens here? You will see this is the general configuration, right? Each germanium will have 4 valence electrons outside and they covalent bond like this. general way of representing it, right? That is the cold bond. Similarly, silicon also, the same way it is happening. Yes. How does energy band form? You'll have a valence band, you'll have a conduction band, and you have different layers which overlap. Yes, that is what you call a band. Energy levels overlap to form a band, and you have a forbidden energy gap between the. You call this energy gap as not merely from this point. Energy gap will be from this point and this point. Yes, the highest of the valence band, the lowest of the conduction band. Acronym for this in some slide. I don't remember exactly. So that is the idea here. Yes. So this difference has to be minimal. There could be cases where you will have different levels in between, in which you dope with something or something like that, which will be seen. And then something we also saw in quantum physics was that we have something called Fermi energy level. Yes. And the motivation for the same is that Fermi energy level lies between the conduction band, valence band, and all that we saw at 0 Kelvin, because the probability of the electron finding an electron is half. So we'll be extending the same concept and proving the same here. So it will be interesting here. Yes. Let's move forward. It is not moving forward. Yeah. Okay. Fine. So what happens? Give me a second, guys. Sorry for this. Yes. So what do we see here? At absolute zero temperature and greater than zero temperature, what happens? Yes. So firstly, intrinsic semiconductors, they are just chemically, naturally present semiconductors, right? Pure semiconductors. And in a semiconductor, the conduction and valence band is separated by a very small forbidden energy gap. We very well know that. And they are extremely pure if it contains one impurity atom out of 1 billion pure. Basically, it is pure. That is what they mean. Yes. And what happens at 0 Kelvin, right? At 0 Kelvin, valence electrons are tightly bound to the nucleus. These valence electrons are present in core. All covalent bonds fill and the valence band is full. There are no free electrons at 0 Kelvin. This means that conduction is empty. Thus, an intrinsic semiconductor is a perfect insulator. Basically, what happens? 0 Kelvin. I very well know that intrinsic semiconductor, or we saw there at 0 Kelvin, above Fermi energy level, you will not have anything, right? And that is why it acts like a perfect insulator, because it does not have any free electrons, right? So if it is greater than 0 Kelvin, if it is greater than 0 Kelvin, you are giving some temperature, right? If there is a case, you are giving them energy in such a way that you can break the covalent bond. If the covalent bond is break, then whatever was initially stabilized in that electrons, right? Electron pairs, they can be broken, meaning they can be free. Meaning, if you provide sufficiently energy, they can come to the connection and they can perform a connection. So, for one free electron present in the conduction band, one vacant site of an electron in a covalent band is created. Correct. So, if that is the case, you will understand that for each electron that goes to the conduction band, there is a hole here, right? So this hole is the hole which we are talking about. Hole is never a physical entity. Hole is merely absence of an electron. Yes. So single event of bond breaking leads to two charge carriers, namely two intrinsic charge carriers in this case, electron and hole. They create an electron hole pair. This is how an electron hole pair is getting generated, right? And energy gap is just the amount of energy required to break that bonding, right? And what happens after that, right? You are not continuously supplying thermal energy. Even if you do, these electrons which have gained thermal energy have jumped to the conduction band, but after some collisions and all that, they'll jump back to the valence band, right? So after thermal generation of charge carriers, electrons move randomly in the conduction and valence band respectively in the absence of an electric field. The free electrons moving randomly in the conduction band may lose their energy on collision with the positive lattice ions fixed in the lattice. Fall into the valence band. Collision nale they lose energy, they'll fall into valence band because of the lattice ions. These electrons merge with holes and you call it again recombination. So they'll combine again. Once they got broke up, now they got committed again. Yes, beautiful. Now the intrinsic charge carriers I told you. So basically the number of electrons which are available is equal to the number of holes that are generated, right? They're equal. So N is equal to P is equal to Na, where Na is the intrinsic charge carrier. That is what I want you to understand. Now we'll quickly jump on the derivation of the density of electrons in the conduction band. So how do you see this, right? So what happens? Let's understand let's break down the graph, right? So what happens? You are representing each energy level in the x-axis, and you are representing the energies itself in the y-axis, right? So what happens when you have you will have a valence band, you will have a conduction band, yes. So you will have a threshold, the highest top of the valence band, you will call it EV always. Top of the valence band is EV, right? And the bottom of the conduction band is called as EC, right? So energy of the conduction band, energy of the valence band, right? Beautiful. And then there is a case that electrons jump from the valence band to the conduction band. All right, right? So you will have sufficiently large energies created in this band gap. Beautiful. There is a Fermi energy level which is in the middle. We are not putting in the middle as of now, right? It is somewhere in between that, right? So let's keep it there, EF. So we very well know when you to find the answer for the charge concentration, right? You have to find energy. To find energy, you have to put it at different places and check, right? We can put it below valence band or we can put it above conduction band, right? So when it is below valence band, obviously we know that valence band is greater than the value E. So in that case, I can just put it as EF minus E, correct? If I put it above the conduction band, obviously it is greater than EC. So in that case, we can write it as greater than EF. In that case, we can write it as E minus EF. Yes, just simple notations. And we very well know EC minus EV is equal to EG. Just few things to note because we'll be seeing the same diagram time. Okay. So I very well told you the density of something is equal to the density of Fermi energy in that interval, that interval. Yes. So in this case, what will you say? Where are you finding? What are you finding? You are finding the density of the electrons in the conduction band only you are finding, right? So in that case, you are only finding the electrons in the conduction band. You need not put the energy down. So in that case, you are only computing from where? You are only computing from the bottom of the conduction band till the infinity. Yes. So your integral limits are going to be EC to infinity. Getting that logic right? Next, what is the density of electrons? So the density of electrons, they are meaning number density of electrons. In that case, I have to find the probability of the electron occupying that energy. That you can easily find that is just 1 by 1 plus E power E minus E by KT. Easy, done. But how will you find the density of states? Yes, density of states. We very well know density of states. What is that? 4 pi by h cube 2 m power 3 by 2 root ED, right? That is what we have derived. So let's keep that also as well. So our formula will go like this, right? We very well know density of states is 4 pi by h cube 2 m power 3 by 2 root ED, but there is a glitch here. What is the glitch? Where are you applying that interval? That glitch is there, right? What happens here? So in this case, energy difference which you are talking about, the interval which you are talking about, right? That is E minus EC. Because you are putting your E above EC, so E minus EC, right? That is the amount of kinetic energy of electron in any energy level E located in the conduction band. That is going to be the energy gain. No, that is going to be the energy which is far more above the conduction band. That is the energy that I'm looking for. Yes. So in general, in this case, you will substitute all the E's as E minus EC. Similarly, there in the subsequent case which we are going to see, for holes, it will be what? EV minus E, right? Because EV is greater, right? So we will see. So yeah, so just remember this 4 pi by h cube 2 over 3 by 2 E minus EC, root of E minus EC dV. Beautiful, right? That is done. Again, this is a very complicated formula. I don't want this E bar something in the denominator. So let's try to nicely put them in a format, right? So you very well know that 1 plus E bar some bigger quantity is negligible, right? So it's far greater. So in that case, I can ignore that one and I can take this E bar thing to the numerator. So in that case, it will become E bar EF minus E by KT. Getting that logic? Yes. So e of minus e by kt was Fermi function, done. De done. Root e was e minus ec power 1 by 2. Very good. Superb. Right? We did everything. But something we lack. What is that? We put everything in terms of ef and all that. Something that I don't know. Right? I know ECEV, right? But I don't know all these guys. So I have to put that in a nice format. How will I put that? So for that only, what do? You write a nice logic. So to take EF minus E, I will add something and I'll subtract something. I'll add something and I'll subtract something. In this case, I'm adding EC, subtracting EC. I'm adding EC, subtracting EC, right? So what happens when I do this, right? Let's understand. And I'm also doing this in such a way that I can solve this integral. Again, I told you there, right? To solve a second order differential equation, I don't know the exact procedure. So I put it in a nice format, that is dou x plus psi by dou x square plus k square psi is equal to 0. And from that, I present that psi is equal to a sin kx plus b cos kx. Right? Similarly, even here, I put this in a nice format and write it to be nice for me to directly write the format. That is my objective. What I do, I'm adding EC, subtracting EC. So EF minus C plus EC minus EC. Now take out all the constants. Take out all the constants. In this case, what are all the constants? The constants is, first constant is EF, right? E is not the constant because you are integrating with respect to E, right? And then one EC, one minus EC, right? I'll obviously keep one EC because I've taken it intentionally, right? So I'll take EF minus EC outside, right? So what happens here? The initial constant 4 by h cube, 2 power 3 by 2. And e power ef minus ec by kt will come outside. Beautifully. Yes. Now what is remaining now? E minus ec already was there, power 1 by 2. E power, what is now there? We observe that we took this guy. We took this guy, right? We took this guy, right? And we'll have ec minus e. Ec minus e does not make sense to me. That's why I put it as minus of e minus ec. Okay, e is better than ec anyways, right? So that's right. And also, there is a form here also, by the way. Okay, so e power minus of e minus ec by kt d. Beautifully, right? Now, if you see this integral carefully, this is a very nice integral actually. Okay, what is this integral? This is an integral of which format? This is an integral of x power 1 by 2 e power minus ax into dx. That's integral of from 0 to infinity. Mind it, it should be 0 to infinity. Okay. Wait. 0 to infinity. 0 to infinity x power 1 by 2 e power minus ax dx. That is my general form of solving this kind of integrals. Right? So what am I substituting to first of all make the limits 0 to infinity? And how am I making this? So what am I substituting? I'm substituting x as e minus ec. So x is equal to e minus ec. So in that case, what would be dx? Dx would be de. Dx would be de. Right? Similarly, what happens when you have to change the limits, right? You change the x and dx, you have to change the limits. But what happens when e becomes ec because the lower limit is ec, right? What happens when e becomes ec? In that case, x becomes 0. X becomes 0, beautifully, right? What happens when e becomes infinity? In that case, x also becomes infinity. Right? That's it. The e variable by that simple integration, right? Substitution limits. Right? So 0 to infinity x power 1 by 2. X power 1 by 2 is minus x dx. This is the general form. Okay? And on comparison also, I get that a. This integral part and all that forms a lot actually. Okay, but I just want to give you an idea of how this works because I didn't have an idea of how this works when I was just obtaining the final answer. And to be honest, that's enough. Okay, just getting to know this how this works is what I want to aim for. So what is this? Whenever an expression of this format is there, right? 0 to infinity x, root x e minus x. The answer is simply root pi by 2a power 3 by 2. Just answer, remember it, right? Root pi by 2a power 3 by 2. Okay, in this case, a is just 1 by kt. So you substitute 1 by kt there. So in this case, it becomes 1 by kt in the denominator becomes kt power 3 by 2. That's it. Okay. So and root pi by 2 is already there.
அண்ணா வாய்ஸ் கொஞ்சம் பிரேக் ஆகுதுண்ணா. அண்ணா
no. இப்போ
ஹலோண்ணா.
இப்போ ஓகேவா எல்லாருக்கும்? மத்தவங்களுக்கு?
ஓகேண்ணா, ஃபைன்.
ஓகே.
Thank you. Yeah. So you got this, right? So now again, I am a perfectionist, right? If that is the case, I would like the equation to be in a nice format, like how we did yesterday, right? So how will I make this a nice format? I'll try to put all the constants together in one thing and put all the variables together in another thing. Okay, what and all is constant here? Temperature is constant, Boltzmann constant, mass of electron, 2 pi h square, all these guys, right? I'll take whatever was 3 by 2 power, I take it first, 2 m kt, I took it all, right? And then pi was there. There was pi power 1, there's pi power 1 by 2, so pi power 3 by 2 is there. There was h cube, remember there, when it was h square per 3 by 2, we took it as h cube outside. Now similarly, this is h cube, parthi vote 3 guru only போட்டுருது. So it becomes h square per 3 by 2 now. Yeah. And then 2 per 3 by 2 becomes what? 2 per 3 by 2 is just 2 per 3 by 2, and there is also a 2 below, right? So now 2 per 3 by 2 minus 1 would be just 2 in this case, right? So just 2. Yeah, there's 4 here. Yeah, sorry. Yeah. So what happens? You substitute all the constants here, right? You eventually get what? 2 into, and the 2 per 3 by 2 just remains inside, right? Just 4 by 2 is 2. So 2 into some whole constant per 3 by 2, right? So let's call this 2 into the whole thing as NC. NC, simplifying the process, NC, right? So it becomes what? NC into E power minus of EC minus EF. I have this weird habit of putting EC minus EF because EC is greater than EF. So that I would at least remember it. Okay, so the final answer would be N is equal to NC into E power EC. Okay, this you have to get the same formula.
Your voice is breaking.
Okay.
Again.
So the format.
நான் இப்ப நல்லாவே பிரேக் ஆகுதுண்ணா.
One second. Give me a second.
Yeah.
Is it fine now?
நான் இங்க கேட்கும் போது நல்லா இருக்கு, பட் ஆனா பேச பேச அது பிரேக் ஆயிட்டே இருக்கு.
இப்போ ஓகேவா?
ஓகே தானா? ஓகே.
இப்போதைக்கு ஓகேண்ணா. Yeah.
So, what happens? NC minus of EC plus EF by KT. Okay. So, is everyone clear with this? Can I have from everyone? Guys? Is it still break?
Light break.
Guys? Ayyo. Just give me a second. One second. Just give me a second. Yeah, guys, I'm back. Is it fine now?
Yes. Fine now.
Fine for now.
Yeah, fine.
One sec. Till now?
Fine now.
Appada. Okay. Let's see. I'm changing my hotspot. ஹாஸ்டல்ல தான் பிரச்சனைன்னு பார்த்தா வீட்டில் கூட பிரச்சனை. ஓகே ஓகே. EC minus EF by KT. This is where we were, right? Now moving on to holes, right? The same logic, we have to find the number density of holes. Same logic, let's apply. What is number density? Density of states multiplied by Fermi energy level. Right, super. I mean, Fermi energy function. So in that case, there will be a slight tweaking in Fermi energy, because Fermi energy talks about the probability of occupation of an electron with energy E. But here we need hold rate. So we need actually not f of e, but 1 minus f of e according to probability. Right? So probability of not finding an electron with the energy E is what is the probability of finding a hole at this region. Yes. So you will do what? 1 minus f of e. Done. And similarly, this will be what? This will be calculated from minus infinity till EV, because you're searching for holes. Holes in the valence band. Valence band is from minus infinity to EV. Yes. So yeah, done. Now what happens? So root E would be what? EV minus E, just like I told you there, right? So 4 pi by h cube 2 by 3 by 2 root of EV minus E dE. Beautiful. Again, 1 minus f of e will be what? 1 minus 1 by 1 plus e power e minus e of by kt. Let's take LCM. So it will give you 1 plus e power e minus e of by kt minus 1 divided by 1 plus e power e minus e of by kt. So in that case, 1 minus 1 will cancel off in the numerator. Yes. In the denominator, you will have something, right? And when you try to cancel out stuff and see, right, you'll automatically see that 1 second. Yeah, and you should also understand that e power ef minus e by k. So in that case, I would just rather take the LCM, see which is smaller, and take approximate. Right. So in this case, it is simply e power ef minus of ef minus e by kt. Yes, beautiful. Just give me a second. It's not loading. One second. Half my time goes in this. Guys, please. Hello. Is my voice clear now? Hello, hello, hello.
Yeah, no. Yeah, continue now.
Okay, okay. Is the screen visible? Okay, okay, thank you. Okay, all right, guys. So we were here, right? 4 pp h cube 2 power 3 by 2 e power ev minus ef. Why did we do this? Again, we were here ev minus e. So I want to put it into that root x e power something format, right? So to give this format, I have to add ev and subtract ev. So in that case, I can easily take e minus ef, ev minus ef, right? And then you will only have e minus ev, which you can take as minus of ev minus e. So ev minus e, the whole root, e power minus of ev minus e by kt. Beautifully, right? So this is of the format root x e power minus ax dx. So a is equal to 1 by kt, same thing. X is equal to in this case ev minus e. And what happens to the limits when you substitute x is equal to minus infinity in this case, right? When e is equal to minus infinity, then ev plus infinity will be there, so x will become infinity. Similarly, when you substitute x is equal to ev, it will become 0. So technically it becomes what? 0 to infinity. So it will be always 0 to infinity. Yes. So we took this nicely. So, and I think they reverse sign somewhere. They should have reverse sign minus infinity to 0. Okay. Did they? Uh, okay. So you have a general format, right? So root x e power minus ax dx. Beautiful. Now what happens here? The answer for this is root pi by 2, 1 by kt power 3 by 2 in the denominator, but it will become kt power 3 by 2. Yes. So general is you will take out the common and all that. You will eventually get what? 2 pi mkt by h square whole power 3 by 2 to e power ev minus ef by kt. I would recommend you guys to remember this as well, right? And this is nv, right? The whole thing. So it becomes nv into e power minus of ef minus ev by kt. That's it. Okay. So that brings us to the end of n and p. Okay. We will quickly see the intrinsic cases as well. Okay. So how does this work, right? Fermi energy level derivation we didn't do still. Okay. So Fermi energy is nothing but what? The energy somewhere in between, but we don't know what it is, right? So we still haven't derived the formula for Fermi energy, right? So how do we do that? So for that only, we are doing the equation n is equal to p. I'm not able to retract it. Is my voice still clear, guys? Can someone react? Is my voice clear?
Yeah, no.
Okay, okay, great. I am not. You are able to see the screen also nicely.
No, screen is not visible. Can you share again?
Yeah. Okay, done. I'm not going to put pen on this. Pen வச்சாதான் இது பண்றோம். Okay, so now it should be fine, all good. Is the screen not visible still?
It's visible now. Continue now.
Okay. Okay. Thank you. So we were here. Very very simple topic. ஒரு 10 நிமிஷம் முடிச்சு போயிடும், அப்புறம் குமரன் தான் பார்த்துப்பான். Okay. So n is equal to p is equal to ni. So substitute the value of n which you have derived, right? The whole term for nc, whole term for nv, and then e power minus of uh, e minus ec and all that. Okay. So in this case we have e power minus of ec minus ef. In this case we have minus of ef minus ev. Yes. So what happens? You just cancel out all the common terms. 2 cancelled, 2 cancelled. 2 pi, all the kt, h square, everything will get cancelled. Eventually, what will you be left with? All the ef, ec, ev, kt, all these guys, right? and KT didn't get cancelled because it was in E power, right? So E power, let's take everything to the left hand side and put only the masses to the right hand side. Okay, so the effective masses of hole is mh and effective mass of electron is me. So mh by me whole power 3/2, that is there. There's a 3/2 here, printing mistake. Okay, so E power, what will be there? EF minus EC minus EV plus EF, right? It will come to the left hand side by KT. Yes. So this will be equal to what? We very well know EF plus EF is 2EF. So 2EF minus EC plus EV by KT is equal to mh by me whole power 3/2. Rest all mathematics only. You just have to derive the EF. From here, how will you derive? First of all, take logarithm because exponential is there. Log of mh by me power 3/2. So 3/2 will come outside. So 3/2 log of mh by me will come. And then KT is there. KT multiply it. So 3/2 KT it will come. Right. And then there is a minus of EC plus EV. So let's put that side. So it will become plus of EC plus EV. Right. And then there is 2EF here. So it will become by 2 in the right hand side for you. Right. So it will give you the answer like this. Right. So it will be EC plus EV by 2 into EC plus EV by 2 plus 3KT by 2 or 4, just check it once, log of mh by me, right? So very well, you can very well understand from here, when you put the temperature as 0, automatically your Fermi energy level becomes EC plus EV by 2. It lies at the midpoint, right? Beautifully. And you very well see that there's this graph where when you have mh greater than or equal to me, that is the effective mass of hole is greater, then it is tending towards a little that side, right? When the effective mass of electron is there, it is tending towards this side, meaning it is decreasing. It's decreasing. Why it is decreasing? The energy is decreasing, guys, because you see mh is greater, logarithm, right? So when mh increases, the energy increases, right? We see that all that, and it lies exactly when in between when EC and EC plus EV by 2, when exactly temperature becomes 0 Kelvin, right? And the intrinsic charge concentration, charge carrier concentration is Ni. We very well know that Ni is equal to N is equal to P. In that case, when you do N into P, N is also Ni, P is also Ni. So Ni square is equal to N into P, right? So Ni square is equal to N into P. You know what is N? Nc into something. Well, you know what is P? Nb into something. Multiply both, take out all the common terms, and you will eventually get what? Somewhere EF will get cancelled out. When EF gets cancelled out, you will get beautifully EG term. EG term is basically EC minus EV. You will get minus of EC minus EV, so it will be minus EG. Okay. So Ni square will be some constant into E power minus EG by 2KT. These graphs are very, very important. You should know the interpretation of all these graphs, right? So you observe that the concentration of intrinsic charge carriers is totally independent of Fermi energy level, right? EF was not there at all in the formula. It strongly depends on temperature. Yes, we very well see that. The concentration of intrinsic charge carriers has an exponential decrease. We see that as EG increases, this guy exponentially decreases and all that. And eventually, what is the electrical conductivity? Electrical conductivity formula is basically Ni into E into mu E plus mu H. Mu E plus mu H, don't worry. This is mobility of electron, mobility of hole. You need not derive anything. E is just the charge of an electron, right? And Ni is the intrinsic charge carrier, which we just derived. The same thing is substituted here with just putting E and mu E plus mu H at the end. That's it. Okay. So that is there. And resistance just 1 by whatever sigma you derive. And obviously, if you observe that, then if you take logarithm of both sides, then it will give you log resistance is equal to log of some constant. It was multiplied, so plus log of something was there. So log gets cancelled out. E power something was there, log gets cancelled out. So it gets Eg by 2KT only, right? So naturally, if you put a graph against log R and 1 by T, carefully 1 by T, you see in your lab journal, you always put with respect to 1 by T. There is a core concept here, right? So log R and 1 by T, if you put a graph, right, then you will always get what? Your slope as Eg by 2K, okay? And your y-intercept will be log C. So that is the concept basically. And this is how it look like, right? So conduction band, thermal excitation, because of that comes 0 Kelvin, there will be nothing, right? At bonus 0 Kelvin, these guys jump. That is the forbidden energy gap, and these guys help. And the slope of the straight line with respect to resistance and 1 by T is Eg by 2K. And with respect to conductivity, log of conductivity and 1 by T would be minus Eg by 2K. Okay, so that is the whole concept for intrinsic semiconductors. I leave it to Rithik for extensive semiconductors. Thank you so much for giving me this. I'll send the voice recording lately. All the very best for your exam. Do well. I'm so sorry. I'm genuinely sorry. I apologize for causing this delay. Personal things plus technical problems. All the very best, guys. Bye bye. Kumara, all the best for the session. Let me know if there's something. Bye, guys.
Okay, bye.
Bye,
Thank you,
no,
Nah.
thank you.
Thanks a lot, no.
Bye, bye.
Bye.
Okay, is my screen visible now?
Yeah,
Do you
Nah.
want break? Do you want break or we'll just wrap it up? Finish it off and wrap it. Break வேணுமா? சரி, okay.
Continue பண்ணுங்க.
Okay, I'll just 60 slides தான். See, you have seen all the derivations by intrinsic, right? The same will be followed in extrinsic. But what you will do, you will take different cases. Okay, well, the same thing as I explained. You know this f of ed, right? This f of ed is basically the probability. Okay, well, why do we take 1 minus f of ed? Because we have talking about concentration of ionized donors. This f of ed talks about what? It talks about the probability that the shell is not empty. Okay, unionized thing. So 1 minus unionized thing will give you the number of probability of the ionized percentage. Correct? So here for the ionized donor, you use 1 minus f of ed. That's why we use 1 minus f of ed here. Okay, the same formula. So the number of ionized donor is equal to density of the impurity atoms in the donor energy level into the probability that it is not occupied by an electron, which we saw above. Okay, this is 1 minus f of ed. Obviously, I've seen about f of ed in the intrinsic itself, right? It's formula. So in this case, you may take 1 minus. So you take 1 minus, use this formula, same. Okay, well, you take in a denominator numerator equalization. And here, once you do this, this one and this one will cancel out. What you do, we have to divide this. Okay, well, you have to divide numerator and denominator by the whole term. Okay, well, am I making it clear? Okay, well, once you do that, you will end up with this term. Okay, well, what you can see here, you will obviously know this thing, na? This numerator is always greater. Okay, well. So this numerator is always greater. So as in the intrinsics we said, it will be always having a value greater than 1. So if something is greater than, I mean, very large, and you add 1 to it, it is obviously negligible, right? Making 1 lakh and 1 lakh 1 rupee is very, very similar. So we approximate it to half to remove this 1 and just keep this term itself. Okay, well? So you get this term. Obviously, making it simpler, you push it up to the numerator by making a power minus 1. So you end up with this. Okay, well, so you have derived what is 1 minus probability. Okay, well, so what now we have to do? You have to multiply with this ND term. Okay, you take this, multiply with this ND term, arrive at a beautiful equation. Okay, well, next.
Yeah.
So similarly, how we derived this, we had ND, correct? Number of ionized donors. Similarly, if you do for NC, we'll also end up with this equation. Okay, well, they will probably not ask you to derive both the thing. You just derive one of the thing and say similarly for NC, you write this. Okay, well. So basically, what is these two different terms now? In case of N, you will have this is conduction banda. You will have a donor banda. Okay. Hello, am I audible?
Yeah, yes, no, yes, no.
That's not audible.
Conduction band, donor band, and also you will have a Fermi level there. Okay, va? So what you are basically doing is you are finding the thing between the Fermi level and the donor level and the conduction level and the Fermi level. So essentially it will make up the whole gap, right? Conduction band and donor band. It will the whole part it will cover, right, these two levels. So that is what essentially you're deriving. You're deriving here the difference between the donor level and Fermi level. In the case of NC, you are doing it with the Fermi level and the conduction level. Okay, both are similar. Just this NDNC and the upper part of the exponential will differ. Okay, so essentially what you will say, this and this are equal. So you will equate these two terms. Okay, as you are here, you have equated terms. So bring the like terms ahead, exponential term, keep it one side, and bring this ND, NC constants to one side. Now, just solve the thing, natural thing. E and EL will add up, ECN and ED will go up into a space. Okay, now I have to remove the exponential. So what you take logarithm on both sides. You will end up in this equation. Just bring the KBT to here. It will come up. Next, what you have to do, just push this minus sign equation this side. Then take LCM and you will end up in this beautiful equation of the Fermi level for N type. Okay, am I clear?
Okay. Yes.
Yes,
Okay.
nice.
Now take a scenario. When this ND is less than, okay, when the ND is less than NC, what does it say? This term will be less than 1. Correct? So logarithm of anything number which is less than 1 will essentially end up in a negative term. So this whole will become a negative term. Okay, so the Fermi level will be affected through this. Okay, in the case of ND and NC. So this part, you know, this thing he explained, right? You are just expanding the NC. You can just keep it as NC itself. That is just the formula of the NC. Okay. Now in this equation, think about this. In case if the temperature is 0, this whole term becomes 0. Am I correct? So you will end up with only this term. What does this say? At 0 Kelvin, the Fermi level lies exactly between the conduction and the donor. Okay, well, that is what it is essentially trying to say. Okay, so then easy points. Temperature increases, the Fermi level falls, because as the temperature increases, this ratio falls less than 1. Essentially, the log would be negative. The Fermi level would fall down. Okay, as temperature increases. See, if you increase the temperature to such an extreme, okay, so like heavy extreme you increase, the Fermi level might even come up to the center of the conduction band and valence band. It can do happen. Okay, so that's what they state. If you like increase the temperature like hell, what happens? The Fermi level becomes equal to an intrinsic semiconductor itself, meaning the Fermi level will match the center of the Fermi level which is present in the intrinsic semiconductor. Okay, is it clear or it's more confusing? Okay, what happens if we increase the doping concentration? If we increase the doping concentration, the same would happen. But as in the case of low concentration, it is falling very rapidly, right, in the graph. Whereas if you have more concentration, it will take a bit amount of time and then fall back, because there's obviously a lot of concentration, right? So the Fermi level would drop slow compared to the low concentration thing. Okay, yeah, here pretty much you have learned all these things before itself. Yeah, this and all we explained. So this is the graph. This is with low concentration doping. This is with high concentration of doping. This goes pretty much slower than this slope, right? Yeah. Next, carrier concentration. So it is same, pretty much simple. You just take this equation we derived there. We derived this equation right there. NC I told the same equation. What you do? Now you got an equation here. Here you have got an equation for Fermi level, correct? You know what is Fermi level, E of Fn. What you do, take the NC term. Yeah, take the NC term and you could find Fermi level in the exponential, correct? This is the Fermi level equation for n. What you do, you just substitute it here. To make things simpler, what you do, get this NC on the opposite side. Exponential goes there, becomes natural log. Then you can substitute to F of E of Fermi level. So it becomes a beautiful equation. You just changes. You just add it up, take LCM. You will end up in this beautiful equation. Next, what I have to do, I have to raise all these on both sides to the power of E. Why I'm doing it? So that I would end up in an equation, because your log is there. I'm raising to the power E. You raise it. E power log of X becomes X itself. So here the term comes down in multiplication, because E power A plus B is essentially E power AB, correct? So essentially this becomes multiplicative term. So this equation comes down. Okay, so am I clear till this point? Okay. This equations come down to the line, and now you have seen that this term is equal to this term. So I'm taking this NC term again now. I'm having this exponential term here. I substitute this here. I get this equation. Root of NC in denominator and NC can cancel out. So ending with this formula. What is this? This is the carrier concentration or number of density of electrons in conduction band. This is the formula. You could see this does not depend on the Fermi level itself. Okay. This does not depend on the Fermi level. It just depends on the concentration in conduction and donor. So this is the catch of the formula here. It does not depend on the energy of the Fermi level itself. This is pretty much NC you substitute, ND you substitute, expand pannulla. That's simple. You just expand, you get into this formula. Pretty much simple. Okay. So effect of doping in okay, what you do, if you increase the doping concentration, the dopants will interact more. If you have more dopants, obviously the dopants will interact more. Correct? What it will do, it will cause the Fermi level to push up. Why Fermi level goes up? Because the donor level would obviously broaden out. So if it broadens out, the Fermi level gets pushed up. So if the dopant concentration is so high such that the broadening of the donor level reaches up to conduction band, the Fermi level will go inside the conduction band itself, as you see here. But there should be heavy doping in that case. We saw about N-type. Now P-type. P-type na tetravalent. So once you have silicon, you have 4 neighbors, right? So boron comes here. It would only support 3 covalent bonds. 1 bond would not be supported. So there becomes a hole, free hole here. So this conducts the electricity. There we saw electron. Here we see holes. Okay, there we call the substituted atom giving the electron to be donor. Here, as it needs electron, it will accept electron. It is called an acceptor atom. Okay, so pretty much simple. So obviously it is focusing on holes. Okay, as we talked about electrons, the donor level were near conduction band. Now this acceptor level will be near the valence band. Pretty much logical, correct? So once these leaves hold, this becomes negatively charged and becomes acceptor ions. Okay, pretty much the same derivation. There we took 1 minus f of e. Here we take f of e. Simple. You just substitute the formula. This is direct formula f of e, right? You just substitute the formula, get it. You will get this. Obviously, as there we did for NC and ND, here we do for NA and NV. So we do for these 2 terms, and obviously they will have the same. We have to equate it, and pretty much same procedure. You have to equate it, bring the exponential sides 1 term, bring this 1 term, take log, blah, blah stuff. You will end up in this beautiful equation. Okay. If you expand this, you will end up in this equation, but keep it simple. Here also, if you make 0 Kelvin, the Fermi level will lie between the valence and the acceptor levels. Okay, pretty much the same concept, only the variables will differ and the band will differ. Okay, pretty much same, only the variable name differs here. Okay, don't fear this, they have just expanded. They have just simply expanded. Okay, instead of EF, they have EV, you keep this. They have just made, they don't want the EF term itself. There we got rid of the Fermi level, right? They're trying to get rid of the Fermi level. There we did the same, right? You can do the same here. No need to expand these stuff and all. This will make it complicated. Okay. Keep it as NV itself. Keep this term as NV itself. NA by NB, pretty much simple. Just simplify. You will end up in this beautiful term in which there is no Fermi level itself. So independent of Fermi level, you get there. Okay. This is just comparisons here. We are talking about the comparisons of the graphs. How it behaves as 0 degree, how it behaves as 300 degree. 0 degree, there's no movement, obviously, no electrons in conduction band, whereas in 300 degree, we get the acceptor ion. This is for end. This is for P. Okay, pretty much simple as we explained about. Yeah. Next, conductivity we already talked about. It is Nu mu, and you can take the E common out. So NP remains there. So pretty much simple. The thing we talked there itself, it is same, pretty much same as intrinsic. Okay, the same steps you follow. Yeah. Here we come on 3 things. Okay, what are the 3 things? Intrinsic range, extrinsic range, impurity range. As you can see, it's 1 by T. So what we have to do, we have to move from right to left. Impurity range, pretty much there. The impurities try to act on. Then the exhaustive range, the temperature increases. Even the things which are in the valence band try to contribute. And in intrinsic range, extreme heat. Every hole has been concentrated. Okay, pretty much same as the N. If you study for N itself, you can write it for P itself. Okay, study one better and just change the variables. Next, mass law action. There we talked about N into P is equal to Na square, right? We are just proving it here. For in N type and P type, this will suit. This equation will suit. What is that? The P into N will be equal to Ni square. What does it say? The carrier concentration of holes and the carrier concentration of electrons in any type of conductor is a constant. And what is that equal to? The intrinsic carrier density. This too is talking about extrinsic. This is about intrinsic. The square of the intrinsic carrier density. Okay, this is the proof. For N, this is the equation. For P, this is the equation. Bring E terms together, bring NC and V terms together, pretty much equated. So here you become minus of ECN minus EVN. What is ECN minus EVN? It is the band gap. So you substitute EG, you get this equation. In intrinsic, this equation is equal to Ni square. So you say this to be intrinsic. So you arrive at this equation. If you do for P also, you will arrive at the same equation. This is just a manipulation of the equation. No issues. Then as we talked at 0 Fermi level, the Fermi will lie between the conduction and donor in case of N. And next, if we make, I mean, there will be a temperature for the donor, complete depletion of the donor level, right? The donor level will completely get depleted. It will release all the electrons. There will be certain temperature. We call that temperature to be TD. Okay, in that case, if the temperature equals to TD, the Fermi level will become equal to the donor level. Okay, pretty much same in the, yeah, this thing is the same I talked about. Okay, whole explanation. Pretty much in the P type. At 0 degree, the Fermi level will between the valence and the acceptor at a temperature where the completely it gives all the holes, which is called the TS. The Fermi level will be equal to the acceptor level. Okay. And if it is, I mean, if you increase the temperature to exponentially high, obviously valence will also lose, right? In that case, the Fermi will become to the half of the whole valence, band gap. Band gap oda half it will change. Same as n. Okay, we have seen as the temperature increases very high, the Fermi level will go to the half of the band gap. So this is whole theory. Okay, here comes all the revision terms. Next, this is important. You know about band gap, right? Band gap is basically the minimum energy. This is crucial. The minimum energy difference. The minimum energy difference between top of the valence band and bottom of the conduction band. This is very crucial, friends. Okay. And now you have seen, like you have studied parallel lines and you have calculated, but that is not the original case. In this, for conduction band, this is the minimum point. For valence band, this is the maximum point. So this is pretty much parallel, correct? So take this point, their momentum is same. So when the momentum is same, the lower of the conduction band 2 occurs, higher of the valence band 2 occurs. I will repeat it again. At a particular moment, you see, this is a moment, this is a moment, this is a moment. At a particular moment, both the upper value of valence band should occur, lower value of conduction band should occur. If that is the case, we call it as direct band gap semiconductor. To formally define it, the top of the valence band and bottom of the conduction band occur at same value of momentum. Okay, wow. If that does not occur, if both occurs in different momentum, as you see, the upper appears at this momentum, the lower appears at this momentum of the conduction band. Difference, right? Not in the same momentum. So you call this type to be indirect, you call this type to be direct. Simple. Okay, now what will happen if an electron should go from this level to this level or this level to this level? It only does a vertical drop. There is no need of energy itself. So what will if it is going from higher level to lower level, obviously it should match the energy level of the lower, right? What will the remaining energy go into? It will go into as photons, which is the light particle energy. But here what will happen? It has to go vertically down also. At the same time, it should displace itself also. Correct? But if it releases a photon, it can only go vertically, which will not land at the bottom of the, the topmost value of the valence band. So we should have something else which makes it to go across. Here comes phonon. Phonon does this job. Okay, what is phonon? It is basically an atomic vibrating packet through a crystal lattice. Okay, well, just that. What it will help? So when an electron goes here, the energy will be used as a heat. If indirect band gap is there, most of the energy will be lost as heat only, not very, very less or negligible amount of light particle, which is photon, would be released. So here what it will do, the photon will make a push here. There will be little amount of energy. So there's a chance a little photon comes out. Okay, so in this case, see, is there any use? Only heat energy is dissipated, no use. No photon is pretty much there. But here photon is there. So that's why indirect band gap is not a significant band gap. So that is why it is not mostly used in the case of industries. All those we use direct band gap because you get a lot of energy through photon itself, right? Okay, yeah. Next. Yeah, why? And also in indirect band gap, it is pretty hard to attain the situation. Why? Because three things: the electron, the photon, the phonon. Three should intersect at the same momentum, and three should be there also, which is a very rare scenario, right? So that is why this thing in case of indirect band gap occurs at a much slower rate. Whereas in direct band gap, no need. It can just make a vertical drop, photon would be released. Pakka. Okay, this it's pretty fast. Okay, for to be saying it approximate, if there is 100% chance and direct band gap does this job fast, 99.9% the indirect band gap would be wasting the energy as in vibrational energy or heat energy. Okay, and this is a whole explanation. Now I taught everything. This is the whole explanation about this. Okay, I've covered everything in this. Next, effective mass. See, inside an electron, inside a structure, see, there will be a lot of minute forces. The nearest element might pull, the whole lattice might pull. There will be small forces. If you account all the small forces, it's very hard. So what we do, we consider the small forces to be considered to be into the mass itself. So that is what is effective mass. Okay, but it is like a fake mass. Okay, but it includes all the literal forces, the amount it could get. That is the physical term why we use this effective mass. Simple da. In E, before what you will do, h dash whole square k square by 2m put. Instead of m, just put m star. M star is the effective mass. Simple. Okay. To derive this m star, what is m star? Just take the kinetic energy equation, h square by k square by 2m star. Just differentiate this term with respect to k. You will end up in this term. Then double differentiate it in respect k. So what you will get, h square by m thing. You need this effective mass, right? So bring it up, bring this differential term down. You will end up in this beautiful equation for effective mass. So this box here, one box is there. Now what it is saying, it might sometimes give rise to a negative effective mass. You might think how mass can go in negative, that to effective mass in negative. Pretty simple. So in case if an electron stays very close to any of the edge of the band will have edges, right? If it stays very close, it will have a higher effective mass. In that case, the force, if it tries to exit, there will be a back scattered force. Okay, well, if something is pushing, there will be a back scattered force, right? When this back scattered force will be more in the band edges. So essentially, this pushing force is more than the going force. It will lead to a negative effective mass. Correct? Because effective mass is concerned with forces also, right? So that's why we get a negative effective mass here. Okay, and also if a particular particle is in the middle of any of the bands, it will have a lighter mass. It is very close to any edge of the bands, it will have a heavier mass. Okay, this is what pretty much explained in this diagram. Teach in all the additional. So this is all the list of formulas you're having. Hall effect. There's no need of any derivation and all. Just understand what is Hall effect. So basically, a Hall effect is when there is a semiconductor or any metal. You are passing a current in it. So a current carrying semiconductor or metal, you should project it to a magnetic field, okay, which is traverse to the current flow. If you do that, there will be a potential difference which is developed, which is normal to both the current flow and the magnetic flow, essentially the fields. I'll say it slow. You take a current carrying semiconductor and you subject it to a magnetic field which is traverse to the current flow. What will happen? A potential difference will be developed, which will be perpendicular to the current and the magnetic field. This is called as Hall effect. And the voltage I talked about now, the potential difference, that voltage developed is called as Hall voltage. So basically what will happen now, when you pass this magnetic field, it will push away the electrons to the side, to the lattice. Okay, so if it pushes now, what will happen? Sidewards push, obviously there will be positive sides aligned one side and negative sign charges will be aligned one side. So there will develop a potential difference. So that's how a potential difference is created when you do this. Charges will be aligned to the sidewards, positive and negative, due to the magnetic field, which is perpendicular. So you will get a potential difference. Okay, this potential difference is Hall voltage, and this effect is called as Hall effect. Okay, and to add an extra information, the charges now, the moving charges, okay, it's not static charges, moving charges experiences sideward forces, right? Because of the magnetic field, it will experience a sideward force, I told now. This force is simply called as Lorentz force. Okay, that's all. This is all additional. This is all what I talked about, but instead these are in formulas, which is not needed for your exams. Okay, this is pretty much all the revisions you will have. This all questions have been discussed in terms of formulas. Okay, so this needs your practice. It will take a hell lot of time if we practice all this. If any doubts, do ping us in the YTS group or personal DM everything. That's all. The chapter is over. Yeah, pretty much that's all. Any doubts,
No doubts, no. Thanks, no.
Okay, da. Hope you all
Thanks, no.
like this session. Thank you. Thank you for.
Yeah, no. Thank you. Thanks a lot.
Okay. Thank you.
Thanks.
Bye bye.
Thanks. Bye
Bye
bye.
bye.